Greetings and welcome. In this session, we will see how to solve the numerical on two-stage compression system with flash gas removal method. So first of all, here the statement we will see, and then we will see about the data which is required. Here, two-stage compression refrigerant system having capacity of 30 TR with flash gas removal is used. Means here this is the capacity of the system. Q dot L 30 TR is given. Minimum temperature of -20 degrees Celsius is given. Now this is a evaporator temperature, so that temperature we use at the evaporator level, and refrigerant type of refrigerant used here is mentioned R22. So here you can see here at this evaporator level the temperature is -20 degree Celsius temperature. So this in the chart, if you see, so here this is a pH chart of R22 refrigerant. So as we have discussed in theory also how to plot the cycle. So this is a 20 degrees Celsius and here is also 20 degrees Celsius. So this line is a evaporator line joining or passing through this point. So this is the temperature given to us. Next to that, what is given when the ambient temperature is of 40 degrees Celsius. So ambient temperature means point on the condenser line. So condenser exit temperature is 40 degree, and ambient means atmospheric temperature, and we consider that in the numerical here the liquid refrigerant leaving the condenser is a saturated liquid, means point number 40 degrees Celsius, this will be lying on the saturated line. The flash tank separate dry vapor at 5 bar. Now this 5 bar is an intermediate pressure, that is a flash tank is in between the evaporator and condenser. So that 5 bar pressure is given. Assume that refrigerant at the exit of evaporator is dry. Dry means condition of compressor entry, point number 1, that is will be on the saturated curve. Compression in each compressor is isentropic, and we have to find here the mass flow rate in each cylinder, power required to drive the system, COP, and piston displacement. So now we will see one by one. So for that we will have to need first of all the diagram, pH diagram, and for that we can see here first. In a brief just I will mention. In a theory we have seen this diagram. So in this diagram you can see the points, point number 1 and 2. So point number 1 will be at -20 degrees Celsius on a chart, because the temperature is given at the evaporator -20. After the condenser, this is a point number 6. Condenser temperature is given 40 degrees Celsius. So 40 degrees Celsius point will be at 6 point will be at the 40 degree Celsius. This flash chamber, that is the intermediate pressure level. So 5 bar. So 5 bar will be the line which is that horizontal line that we'll see in the pH chart. So in this way, now in a pH chart, if you see, this is a plot of the multi-pressure refrigeration cycle, that is a flash gas removal method. So here point number 1 you can see, here point number 6 condenser you can see at 40 degrees Celsius. This is the intermediate pressure line at 5 bar. So this line will be extended. Then this 6 point when we get, we draw this line. Then we drop vertical line, that is the expansion. Then from 8 also we drop this line. 20 degrees Celsius, this horizontal line and vertical line will meet to each other. Here we will get point number 8. Here point number 1, through this point, these are the isentropic lines. If you see, you can take reference line to isentropic lines, and you can draw a line or curve which is parallel to this isentropic line till this till it will intersect to this intermediate pressure line. So here intersection point, this point you will get that will be exit of the compressor 1, low pressure compressor point number 2. So in this way you can locate the points. About the point number 4 we will see after the calculation, because point number 4 is not on a saturated line. So on a saturated line, point number 1, point number 3, point number 6, 8, these are on saturation line. So all these enthalpies are mentioned here, which are obtained from the chart here, and these enthalpies we will enlist there in the next slide. Again 6 and 7 enthalpy will be same, because isenthalpic process in an expansion valve in an upper envelope. This is an expansion valve before the evaporator. This also H8 and H9 enthalpies will be same. So here now you can take all the enthalpies here. This is a pH diagram schematic we have drawn here. We have shown here all the points and corresponding enthalpy 1, 2, point number 3, 6, 7 and 8, 9. These are the enthalpies directly obtained from the chart. We need specific volume of compressor entry, that is point number 1. So this specific volume we obtain from the chart in a meter cube per kg. This will be used in a further calculation. Now we are given cooling capacity 30 TR. So this 30 TR capacity we will use in the further. Here you can see Q dot L. That Q dot L formula we have modified. This part already we have seen in a theory. So M dot 1 is a formula equal to what? Q dot L divided by enthalpy difference across the evaporator. Now here the Q dot L is given in TR. So that is why this TR value you have to convert into kilowatt. So for that you use this multiplier. So 30 multiplied by 3.517 divided by this H1 and H9 enthalpies are put here. When we do this complete calculation, we find the M1 dot in a kg per second, that is what mass flow rate which is getting circulated in a low pressure compressor C1. Then for the mass flow rate in a high pressure compressor, that is a compressor number 2, this is a formula that already we have seen in a theory session, theory video. Here this formula we write by using enthalpy balance equation, energy balance equation at the flat chamber. So this formula, in this formula, M2 dot S7 is equal to M2 dot minus M1 dot bracket complete S3 plus M1 dot into H8. Now in this formula, M1 dot we have obtained, that we put here, and the enthalpies S7, H3 and H8. These enthalpies are obtained from the chart which we have listed in last slide. So we put all these value here is unknown only M2 dot. So by doing this calculation and simplification of the this step, we find the value of mass flow rate of the compressor 2, that is high pressure compressor M2 dot in a kg per second. So in this way we got the mass flow rates of the both compressors. Now we can use these mass flow rates further for the next calculation. So as I mentioned that point number 4 is on the chart coming between point number 2 and 3. We don't know exact location of that point 4. For finding that point 4, in theory session we have this formula. This formula we got by using the energy balance equation concept at the compressor, high pressure compressor entry. So this is the equation, M1 dot H2 plus M2 dot minus M1 into S3 is equal to M2 dot H4. Now in this equation, value of mass flow rates M1, M2 dot, that we have put enthalpies from the chart H3, H2, H3, and we have put here H4 we have to calculate. So we arrange this equation in the form of H4. By calculation we get H4 enthalpy in kilojoule per kg. This H4 enthalpy we use to locate that point on a pH chart. So on a pH chart, H4 4140.07 means 414. So here you can see this is a 400, this is a 410, 420. So here after 410, here will be that value. So from this we go in upper side here, and 414 means here it comes in between 410 and 420. So with taking this reference, we go here upper side, and here we can locate the point, that H4 point here, this point number 4. So in this way, by using calculated enthalpy, what value we obtain, that value from the scale we locate, and then after we draw the line, compression line of compressor 2, that is high pressure compressor. To draw this line, same method which we use to draw 1-2 line. So in this way you draw this line will intersect to this condenser line which is at the upper side, and here we will find the point number 5. Point number 5 enthalpy we can read here near this upper side. Here is the enthalpy scale, so we can see here 440 and 2 divisions, so it comes 442. H5 value is 442. So this value we use in the. Now this value depends on, means clarity or correctness of the value depends on the individual person, how that person is drawing that line, how that person is taking that line in upward direction. So that is why here H5 value now we will use for the calculation. In the calculation now we can see compressor power. So for the compressor power, here are the two compressors. W1 dot formula is M1 dot bracket, enthalpy difference for first compressor is H2 minus H1. So here all the values H1, H2 we know, M1 dot calculated, putting this value we find this power consumption of the compressor 1, low pressure compressor, W dot 1. W dot 2 high pressure compressor, formula is M2 dot into for the compression second enthalpy difference H5 minus H4. Here we find the by putting the values, means mass flow rate and enthalpies, we find the consumption for the compressor 2, W dot 2. Now these both consumptions we find in a kilowatt. So net power consumption means power to run the system will be what? Summation of these two values. So summation of two values comes in a kilowatt. That is a power required to drive the system. Now COP means coefficient of performance of the system, that is what? Ratio of output to input. Output means cooling effect and input means this net power consumption. So cooling effect in a TR, that convert into kilowatt, so 30 multiplied by 3.517 divided by net power consumption, what we have calculated here in a kilowatt, that we put here, and then we find the COP value, coefficient of performance. So here we have calculated compressor power. Now next to this we are asked to find the volume flow rate, that is piston displacement. So fourth point in the numerical was to find the volume flow rate, piston displacement. Now here for that we need a specific volume, already we have discussed about. So here this is a specific volume V1, the V1 meter cube per kg, unit of specific volume which obtained from the chart, and this is a process 9 to 1. So here is a entry to the compressor 1. Now this we can put in the formula. So for the piston displacement, here you can take the formula. Mass flow rate is in a kg per second and specific volume is in meter cube per kg. So if you take product of both, then kg get cancelled and we find meter cube per second. That is what volume flow rate or piston displacement. So that is why here we write the formula M1 dot into specific volume V1. M1 dot mass flow rate, V1 from the chart, taking product, this is a answer. This answer is in meter cube per second. Now in the numerical, sometimes it is asked to mention that in meter cube per minute, or sometimes it may be asked to mention in meter cube per hour. So as per the requirement, you can convert it meter cube per second value. To convert that in minute, you have to multiply it by 60 because 1 minute contains 60 seconds. And to convert this value from second to hour, you have to multiply this value with 3600 because 1 hour is equal to what? 3600 seconds. So as per the requirement, you can mention the piston displacement value in meter cube per second, meter cube per minute, and meter cube per hour. So from the numerical, we have seen that how to solve the numerical, how to find the values, and in this numerical, we have obtained the first answer, that is a mass flow rate in each cylinder, means compressor 1 low pressure cylinder and compressor 2 high pressure compressor. That was the first. Second was asked, that is a compressor consumption, means power required to drive the system. So net power was what? W1 dot plus W2 dot. W1 dot for low pressure, W2 dot for high pressure compressor. Third one was coefficient of performance, and fourth one piston displacement at the entry of compressor low pressure. So in this way we calculate, we have seen how to solve the numerical and get all the values from the statement.